Hi everyone, welcome to my channel. So in the previous video we have discussed about matrix vector multiplication and linear transformation. In this tutorial we will see some properties of linear transformation. Here is a quick recap of what we have seen in the previous tutorial of linear transformation. What does it mean is, suppose these are my original x and y axis, and suppose this is I hat and j hat, the standard basis vector of this original space. Now applying a transformation to this space is equivalent to matrix multiplication on the vectors in this space. So if we just rotate the plane somehow, we can see that after rotation the origin should coincide. After rotation, where the I hat and j hat land in the new space. So this is suppose my new space, and in the new space, what is the position of this I hat and j hat? And I'm just showing you the rotation because I can't do this much animation in the PowerPoint. But you can see we have seen in the previous tutorial different applets which were giving you flexibility to, and yes, we can also enlarge or this thing, but keeping the origin fixed at this thing. So we have seen in the previous tutorial some of the animation where we were able to change the matrix of transformation here, and we were able to say where these vectors land in that particular applet, or we have seen this kind of graphics there where we have seen where the coordinate lands, and we have seen this calculation there, right? Now here in this particular tutorial, this is for math student who would like to see the formulas and how the computation works when we talk about linear transformation and their relations to matrix vector multiplication. So you might recall it from the previous tutorial discussion. Suppose this is a matrix A which has the elements A, C and BD in these columns, and this is the vector. I have given it a name U, and we want to see that after multiplying this matrix with this vector, what would be the product of this vector. So this would be some other vector V, right? So we have seen in the tutorial of matrix vector multiplication how to compute that, and we were able to get this result AX plus BY and CX plus DY. If you have not watched those tutorials, you can go back and watch that first. In the next tutorial, we have also talked about that if it is a matrix, if it is a vector, and we want to see where it will land. So instead of doing the computation, what we can do is we need to see where the I hat lands. So I hat means the basis vector from the original space. So this is the column which represent where I hat lands in the new space. I hat lands in the new space. And this column represent where j hat lands in the new space. After doing that particular transformation, whether we are doing rotation, shrinking, flipping, whatever, right? Or basically we can say these are the coordinates of I hat and j hat in the transformed or in the new space, right? Initially we know that I hat has the coordinate 1 0 and j hat has the coordinate 0 1. So after doing the translation, this becomes AC and this becomes BD vector. And we write these four things in the form of a matrix which represent the transformation, right? So what we can do is we can simply multiply x with the vector where new I hat lands and y with the vector where new j hat lands. And this is exactly equal to the same calculation which we were receiving when we were doing matrix vector multiplication. So what I mean to say is that if you want to see the position of any vector in the space after applying a certain transformation, what information you need is you just need the information about the transformed position of I hat and j hat. I am saying I hat and j hat, but it means the basis vector which you are using in your original space. For example, this is your xy axis and you just want to rotate it anti-clockwise. Anti-clockwise means like this, 90 degree. So it means after the rotation, it means I hat originally, this was your j hat originally, but after the rotation it will switch the position. So you are doing 90 degree anti-clockwise, so it means your new I hat would be here. So this would be your new I hat. The purple line which I am doing, this would be new I hat, right? And the coordinate of new I hat would be 1 and 0. Your new j hat would be here because this y axis would be now at this line. You are rotating 90 degree anti-clockwise, right? So your j hat, its new coordinate would be -1 and 0. So these are the two things which you need to understand or explain this transformation. And if you write it in the form of a matrix where the first column represents the position of I hat and second column represent the new position of j hat. So this is your transformation. And just by using this transformation, you can find out position of any vector in the new space. So suppose the vector was at 5, 4 in the original space. So it will land at 5 multiplied by where the I hat lands 1, 0 plus 4 multiplied by where the j hat lands -1, 0. And the position would be 1 and 0. And this thing you can verify by using that applet. Oh yeah, just a moment. I did something wrong here because the new I hat position is at this point. This is 0, 1. My bad. This is 0, 1 because x coordinate is 0. And the new one is -1, 0. Let me correct it. 0, 1 here. And if I do the math again, this is -4 and 5. So if you want, you can verify it with the applet. You can see that 5, 4 lands to -4 and 5, which we were seeing in the presentation also, -4 and 5. And those who are from mathematics, they can understand it or they can relate it with functions. You might have read functions which maps from one space to another space. Now, this is very similar to that notion of functions. We can represent transformation by the notation T. For example, you can represent transformation as capital T. This is basically a mapping which takes m dimensions input and maps them to n dimensions input. Rm and Rn represent the space of real numbers in this dimensions. What it basically means that your input space is all the vectors which are of dimensions m, right? Input space m vector and your output space is n dimensional vectors. So we have never said that the transformation only works when the vectors dimensions is the same. We have seen the example in only 2 dimensions where the input vector was also 2 dimension, output vector was 2 dimension because it was easy to visualize. And even for 3 dimensions you can look at some animations which show you how 3 dimensions transformation works. But we can have different dimensions also. So for having this kind of transformation to work, suppose this is your input space where you have all the vectors of m dimensions, and this is your output space where you have vectors of n dimensions, right? So to be able to map these two together by using the transformation T, you need to use a matrix, and the matrix would be of dimension m cross n. If you are having trouble understanding m and n, you can just understand it with a simple example. Suppose you were having a matrix which was 3 by 2. So suppose 3, 2, 6, 1, 2, 5. And you want to apply this matrix on a vector. Then vector must be having 3 rows. So whatever it is, suppose 10, -5 and 7. These are the elements in the 3 rows of the vector. And the output vector, when you do this kind of calculation, what would be the dimension of the resulting vector? Can you visualize? You will multiply the first row with this, there would be just one element here, and you will multiply this with this column and there would be just one element. So this would be a 2-dimensional vector. Now I hope you can easily visualize that your matrix dimension is 3 by 2, your input vector dimensions is 3, and your output vector dimensions is 2. So this is m, this is n, and this is m by n. For this particular transformation, we have not seen the visualization, but you can now imagine that input is 3-dimensional. So your original space is 3D space, but after applying this transformation, the output space is 2-dimensional, right? So we are reducing the dimension. One dimension is shrinking. And usually when that happen, I need to change the entries here. Usually when it is possible to have the result in lower dimension, this is only possible when one or more columns of the matrix are redundant or linear combination of other. Like we have talked about linear dependence earlier too. We can see in this matrix, this is 3, 1 and this is 6, 2. So these are giving just the same information. These are The third column is the linear combination of first column, or we can say the same thing for this also. So in this case we can have lower dimension. So we will talk about this once again when we will talk about rank and all. But yes, I want to convey that we can have different dimensions here. Now we want to talk about the properties of linear transformation, why it is linear. Transformation means very similar to function. You can relate it to function or a mapping or kind of a movement of your original space. But what do we mean when we say linear? Now when I say linear, many of the students just relate it to equation of a straight line y equal to mx plus c. But let me tell you, this is not a linear transformation. This is affine transformation. So if you are not sure, you can work around on this example. I will show you the property of linear transformation. You can play around with this equation and you can answer this quiz, why the equation of a straight line is not a linear transformation. This seems contradictory initially, but once you understand the properties of linear transformation, you will be able to easily prove that it's not linear transformation, right? So the property is, if you apply the transformation on linear combination of vectors, listen to it carefully, linear combination of vectors. Now I am writing it just for two vectors to make it simple. We can generalize it for as many vectors as we want, but I don't want to scare you. So these are my vectors. And what do I mean when I say linear combination of vectors? It means that we have talked about linear combination of vectors earlier when we have discussed scalar vector multiplication and vector addition. So if I have these scalars a and b, I do scalar multiplication and then I add, this becomes the linear combination of vectors, this term right here, right? So linear, what happens when I apply the linear transformation on linear combination of vectors is, you might have guessed, this is a, then transformation of the vector u, plus b, then transformation of the vector v. So what exactly this term is, we can say that this term is linear combination, because we are doing a scalar multiplication and addition, linear combination of transformation of vector. I hope you are getting it. So this term right here on the right hand side is linear combination of transformation of vectors. And the entire term on left hand side, if I say the entire term, this would be transformation of linear combination of vector. So in whatever order you do, if you apply the transformation first, then do the linear combination, or if you do the linear combination first, then do the transformation, it is same. So I have written one single property, or maybe if you are having trouble understanding this property, you can break it into two simple parts, that if we apply the transformation on sum of two vectors, it would be tu plus tv, means the transformation of vector u plus transformation of vector v. This is one property. And another property would be t, if you apply on scalar vector product a of u, it would be a of tu, transformation of that vector multiplied by that scalar. So you can break it into two smaller equations if you have trouble understanding the bigger equation, but if you are from math background, might find it just another way of writing these two equations in one single go, right? So this is mathematical property of linear transformation. And if you have right applet or animation, you can visualize this thing where you have two vectors, you do some linear combination of those vectors, then you apply the transformation, and you can play around with these things. Or otherwise you can prove these things either mathematically using the proofs, or you can prove these things by using some libraries where you are finding out linear transformation and you can verify this property. But the idea is to understand why we call it linear, because this property holds good. Now one more thing I would like to tell you about, if you are from math, you might be able to recall what you have understood in functions, like sorry for the bad drawing, this is your input space and this is your output space. So all those terminologies which you have read in context of functions are applicable in context of transformation also. So this is domain of the function, this is codomain of the function, and you can say input space and output space for the transformation. Now we can see that vectors in the input space will be transformed in the vectors in the output space. So the set of all those vectors which get transformed by using the all vectors from the input space would be known as image of the transformation. Like you say image of a function, so it is very similar, image of t, right? And we may have the image set equal to the output set, or we may have image set as the subset of the output set, depending upon how is your transformation defined. So in context of function, you might have studied the definition of injection, surjection and bijection. Those definitions are applicable here as well. So if your transformation is bijective, your and you are saying it is a transformation from Rm to In. In case of a bijective transformation, M would be equal to N. And if you are not sure what I am talking about, it looks like some other language to you, just go back and brush up the concept of functions or transformation which you have read. If you want me to explain injection, surjection, bijection, ask me in the comment box. I will prepare a short video for that. And one more thing is that in every space origin, the coordinate 0, 0 would always be there in both the input space and output space, right? So if there are multiple points in the input space which transform to the origin point, right? If there are multiple vectors which translate to the origin point in the output space, then the set of all those points is known as kernel of that transformation. So I'm not writing the typical mathematical definitions here. If you prefer using those definitions, you can refer to the standard textbooks along with these videos. This is just a quick revision of conceptual things, and if you are preparing for some interview and they are asking you something in concept, so you should be able to understand, answer those concepts. What is a kernel? So kernel means the set of all those vectors which after applying a linear transformation maps to the zero vector, right? Now in the next tutorial we will talk about rank, dimensions, column space, null space, these things which are basically related to M and N, the dimensions of input space and output space, right? So we will be covering these topics in the next tutorial. Stay tuned. Thank you for watching.